So good morning everyone. I welcome you all to the next technical session of this FDP. Now I would like to welcome Gaurav Singal sir. He is an assistant professor in computer science and engineering department at NSUT Delhi for the next technical session on GANs, face detection, graph neural network, web deployment of AI models. Gaurav Singal sir is an assistant professor in computer science and engineering department at NSUT Delhi. He obtained his PhD and MTech in computer science and engineering department from Malviya National Institute of Technology, Jaipur, India. He received the research grant from Department of Computer Science and Technology, Uttar Pradesh on women security and development of biotechnology on assistive device. He is actively working in research and teaching from last 9 years and published number of reputed conferences and journals. He is the member of Scientific Society IEEE and ACN. He is a certified as NVIDIA Deep Learning Institute Ambassador and UiPath RPA Advanced Developer. His research interests include wireless and ad hoc networking, Internet of Things, edge computing, applied deep learning, and reinforcement learning. Sir, I welcome you to this technical session.
Thank you, Madhuji.
Thank you, sir. Sir, over to you for the technical session.
Okay, thank you. So, good afternoon, guys, and thank you, Ms. Madhu, for giving a detailed introduction about me. And I think 3-4 topics are mentioned with my name, but today I'm giving only about the GNN, its graph neural network. So let me share my screen and then I can start. I think my screen is visible now.
Yes, sir.
PPT also.
Yes, sir.
Okay. Okay. So yeah, it's like you mentioned 3-4 topics. So I thought like I can choose some slightly advanced topic, or you can say new to all. I don't think so. Like you guys have already heard about that or you worked about on graph neural network. So I also tried the first time, but like I thought like why not give something new to the candidates who are attending this FDP, because I think we already covered CNN, RNN, object detection, and like advances of all these models. So slightly it's the different one, just like basic of you can say CNN and RNN they have taken and they have thought how graph can be input. So just to like introduce, okay, first of all, it's I think this is me, Dr. Gaurav Singal. I think it's already covered, and this is my web page and my social media handle. If you guys are interested to collaborate or do any work with me, please contact me over email ID or my LinkedIn page. So before the starting of session, so what I will cover in this session, so why GNN, what is GNN, how it is useful, what are the requirements of this GNN over CNN, RNN, you can say convolution neural network, and ANN, and recurrent neural network. So basically what they are taking input, simply in the form of image, or you can say sequential data. But suppose if you want to input a graph, then will this model or will this existing work will be good enough for processing that, or you can say for classifying that, for segmenting that, for predicting that, for any kind of operation, is it suitable or not? So passing a graph structure is not possible with all these existing networks. Okay, so that is the way, like what are the different models in GNN. So I will try to give you a brief overview of that, and finally I will try to just summarize of, you can say, a short notebook file of Jupyter with GNN to give a flavor on that. So basically you can say this my session will help you to get an introduction of GNN, and if you are interested, so it will give you a flavor, then you can study more, and because this is a very big topic, we cannot cover in a such short time. Okay, so the first thing is why network. So basically, what we are going to till now, like we have passed them some data of weather forecasting. We are passing 100 number of rows, 1,000 number of rows, or you can say million number of rows. Okay, and in some kind of image classification or like person classification, face detection, we are passing some 100 number of images or 1,000 number of images. That is a different kind of problem. But what is the scenario here? So suppose we want to pass a problem of, you can say, road transportation. So road transportation, you cannot put it as a kind of structured data. So it is like a kind of a graph, or you can say network. So this is not like a fixed kind of image, fixed kind of sequential data. So that's why you can say that all the complex problems can be solved with the help of network. So we need a network. I think you all have studied the network, what we are using in the our computer network course, or like what do you mean by networks? Network is simply, if I'm saying, so it's containing two things. One is node, and second is edges. Okay, so there could be multiple meaning of that is existing. So node can be represented by the entity or a person or any other thing, and edges could be represented by the relation of two person, relation of two companies, relation of client and user, client and user. So different kind of relation could be exist. So this structure is called network. I think it's very basic thing. So you can say these are, you can say it's a kind of node, entity, person, maybe some destinations, anything. Okay, and in between, if you're putting some kind of connection from one to many or one to one or all, so then it could be called as a network, or you can say it could be called as a graph. This is, you can say this is Z, or you can say N network. So it's combine a set of vertices and edges. So vertices are, so you can say V1, V2, V3, V4, and this is E1, E2, E3, E4. So this is, V is a set of vertices and E is a set of edges. So this kind of network is, I think you already have studied. So the thought is how we can pass this data to our neural network. So suppose this data is giving you a significant output or significant number, or classifying some idea, some data, then directly putting a picture or directly putting this specific information is not able to solve our problem. So we have to find a way in which we can pass complete information of vertices and edges to a neural network model that help us to classify, predict different kind of operations. So there are multiple data are network are available in the market, or you can see in the near places. So one you can see social network, like you can say it's a kind of Facebook, or you can say LinkedIn. These are all social network. So one guy can be connected with other guy, like so, and there could be possible different kind of relations. One is friendship, one is colleague, one is a relative. So there could be multiple kind of relation possible with this kind of network. Second is information network, or you can say web and citation. So there are some documents are there. One document is linked with another one. One link is transferring with another link. Okay. Second, you can say economic network. So suppose some transaction-based networks are there. Or you can say, you can take example of blockchain also. So like you have a multiple transactions with different nodes for verifying the transactions. Okay. Next could be in biomedical network. So you can say this is a very famous application in graph neural network for discovering drug discovery. So for specific disease, you want to discover a drug. So you can use this GNN for discovering drug also in biomedical network. And you have a network of neuron and internet. Internet is example. Internet is simply, we are saying internet is equal to network. So it's also an example of network. So these are the networks we have. And if we are able to pass this information and we want to predict something and we want to classify something, then will this previous ANN or CNN or RNN will be suitable? So that we can, so to avoid that thing, we are using GNN, graph neural network. So again, like why network, why now? So basically it's a universal language for describing complex data. So like road network, road transportation, internet, we cannot explain with the help of linear and structured data. So it's kind of graph or network data. So basically it's sharing vocabulary between field, and there is also data availability. So it's also computationally challenged, and it's also have impact. So we can easily we can say find some kind of inference with this kind of data, with this kind of graph and network. So like it can be used in social networking, drug design, and social media. So if we are applying machine learning with this network or with the graph, so we can do different kind of tasks. So like these kind of classical tasks we are doing. So we can say we are doing node classification. So basically we are predicting, you can say a node, or you can say node value, or you can say node type with this node classification. Second could be we are predicting link. So whether these two entities, they have any link or not, whether they have any connection or not. So what I think LinkedIn is doing, they're able to find some kind of mutual friends or like a mutual connection in between two guys. Okay, so that can help us to find a what is the probability that they have a link in between two nodes. Okay, next could be in community detection. So like you want to identify a densely linked cluster of nodes, and also for network similarity, how two networks or how two graphs are similar to each other. So that is also will help us with machine learning. We can try to find how these two networks are similar. So this is the example of node classification. So suppose this is your input graph, and we want to find what is the type of this node. What is the type of this node? So suppose we have a two kind of node. One is yellow and what is green. So to predicting or for classifying this node type, we can use this GNN, a graph neural network. So you can say we are predicting this one is green, this one is yellow, this one is also yellow, this one is also yellow again, and this one is also green. So we can pass this kind of structure to find the node classification. Okay, so basically you can see if we have this kind of molecule or this kind of structure in the interactome, okay, so then we can use to find the functioning of a particular protein. So what a particular protein is doing in this scenario or in this example, so that we can help us in this application to classifying the functioning of protein. Next could be you can use it for link prediction. So before that we are classifying the node, and now we are predicting the link. So what I given you example, so like two friends are there or two guys are there, is there any possibility to have a connection in between that? So you can see it's not like by randomly you can say yes or no. They have to see their common patterns. What are the common patterns in the node? So like what are the features of each node? So based on the features of node, we can predict there should be a connection or not. Okay, so these kind of things can be easily taken care by this network. So you can see this example is there. So suppose we have a graph in between, like what are the product they have already bought and what are the product already available with website. Okay, so based on previous purchase, we want to identify, or we want to find what could be the next purchase for the particular customer. Is there any possible relation that after this he will buy this product again? So you can say in recommendation system we can use this kind of link prediction. Or you can say it could be like, yeah, after this he should be search for that link. So you can say searching a link also could be a link prediction application. So you can say, like, I'm giving you like some basic applications. So when you are going in details, there are so many applications or real-time applications people are using or using for this GNN, graph neural network. Okay, so just like introduction, I hope you already cover machine learning, deep learning, what are difference in machine learning and deep learning, what CNN is using, what RNN is using. So just background for that. So machine learning basically is supervised network machine learning life cycle. So this feature, that feature, every time all features we are discussing. So before that we are taking raw data, then we are doing some kind of pre-processing, or you can say feature engineering to convert into structured data. Then we are applying some kind of learning algorithm. So there are multiple learning algorithms are available in the machine learning. And based on that learning, we are generating a model. So for this, we need a feature engineering. Nowadays, we don't have it required to do feature engineering. We have a scope of deep learning so that we can automatically learn the features from raw data. So automatically, if we are able to find the prominent features from the input data, so that we can say help us in our classification or prediction of the process, and also it will fasten the process. It will take, you can say, because feature engineering, again, people will say, a person will sit and will try to find what could be the prominent feature. So all these things can be done automatically without any human intervention. So yeah, so feature learning in graph, how can we do it? So for that we need kind of embedding thing. So the goal basically efficient task independent feature learning for machine learning in network. So how we can do efficient task independent feature learning for machine learning? So basically, if we are getting a graph, so how we can pass a graph to the network, or you can say CNN or ANN. Okay, so passing a graph, we have to first make a vectors, or you can say make a metric for all these nodes. Okay, so first of all, how we can make a vector for a particular node. Anyone know how to like convert a node to vector? If they have studied some kind of RNN or node embedding. So basically there are multiple algorithms are there. So we'll not discuss that part in the detail because that is a separate topic also. So we want to generate, or we want to give a specific code for a particular vector. So generally we are saying it's node embedding, or you can say there's a function is there, node to vector. So what will happen? There is a function in which we'll pass a function u. It will give us a vector of particular dimension, a particular depth, you can say. Okay, so you can say, like, if you are putting u and we have a vector of suppose 6 elements, so we can put some information and you can say this location is defined for u, so this will be the vector of this u node. Okay, similarly, if we are generating for this v node, there is again a position will be fixed. This is the 1. Okay, but then again you can say there are multiple methods are there, because with this kind of formatting of 6 block, you can only assign 6 nodes. If you want to assign more node, then why can't we? Why we are starting with 0, 1? Why can't we give a value? You can say range from 0 to 255. So you can say like it is 0, 10, 0, 15, 0, 0. So this could be a vector for the or this the vector for the U node. So there are multiple methods out there that help us to generate a vector for a particular node. This thing we are doing when we don't have any fixed value or any input feature for a particular node U. If we have already that, then we are not doing this kind of feature learning or node embedding. Then we are again coming to next part, why it is hard with the already existing model, why we need separate kind of structure. So model deep learning toolbox is designed for simple sequences or grid images. Simple sequences or grid images. So you can see CNN are using for classifying the image. So what this image is containing. So we are using, we are passing into maybe MNIST data set we are passing, and we are predicting this is 3. So you can see it have fixed image size 28 cross 28, maybe something else. Okay, so we have a grid. You can pass into some kind of CNN network, and we can easily able to find the class. And maybe if you are doing those MNIST, so you can find a character class. What is that? Okay, and similarly in RNN or word to vec for text sequences. So basically we have some kind of text. So that text or basically string we can convert into some kind of useful information, or you can say predicting the next word or predicting the caption, predicting the like the summarization. There are multiple applications there, but in all the cases you have a kind of sequence of strings that can help us to pass in LSTM. I think most common model people are using it, or you can say GRU, get recurrent unit, to predict the future data or predict the output. So, but in the network case, it is far more complex than what we are doing with CNN and RNN. So, the first of all, it's a complex topographical structure. This is no spatial locality. The location is not fixed. If we are saying this image is there, this image look like this one. And if we are seeing graph, we don't know in which dimension is going. No fixed space, no fixed structure. So that is not possible to apply to pass this kind of data in that structure. Okay, no fixed ordering, no fixed node ordering. So sometimes you can start with this node, sometimes you start this node. If I will slightly move in some other location to this same graph, suppose I am saying this way, this is a graph. If I am moving slightly in other direction, so it could be this one also, it could be this one also. So all these have same thing, but just slightly moving, it will change the representation view. Okay, so this is the like isomorphism problem will be existing in this kind of data. And often it is dynamic and have multimodal feature. There is no fixed feature is there. It's a multimodal feature. We'll tell you what is the effect of node ordering in the coming slide. Yes, I think it just came here. So how we can represent the graph, if anybody know, in terms of code. What are two methods to represent graph? One is clearly mentioned here, adjacency matrix, and second is my voice is audible now? Anyone can give me
it's audible.
Yes, sir. You are audible.
Okay. I think somebody has a issue question also. I think somebody is raising their hand. Oh, I think it's gone. Okay. One is adjacency matrix and one is adjacency list. So I will not go detail what is list, what is matrix. So basically, again, if you are choosing the list, so it is again a dynamic thing. It's generated according to the requirement of node. It could be smaller, it could be bigger. Okay, but we want a fixed structure. So that's why we are converting it into. We are using it a adjacency matrix to represent this graph. So I think it's not a new concept for you guys. So we are just making a adjacency metric. So what could be the size of metric? So it's simple. How many nodes? 6. So 6 cross 6. Okay. So if you are suppose you are starting with A, B, C, D, E, F, then this is the structure. From A to B, there is a link. A to C, there is a link. A to D, there is a link. And A to E and F, there is no link. So this is the kind of adjacency metric for this graph. Okay, so you can see if I am slightly rotating, or I can say rotate completely, then actually there should be no difference in adjacency metric. But suppose now I'm again saying a person to calculate the adjacency metric. So what he will do, he will assign the order like this. Okay, sorry, I mentioned again. So in this case, first we found F to F 0 because there's no self loop, so we can directly put 0. So F to E, no, I don't have. F to D, yes. F to B, 0, 0. So this kind of structure is there. When I will match with this structure, is it same? Not same. So again, this kind of issue also exists if we are passing this kind of data to that kind of model. So that's why I'm saying if we are doing reordering, then this will be the difference in the input features what we are passing to the network. So this is the GNN. So GNN need an architecture for machine learning on graph structured data. Also need to take advantage of structural relationship in graph similar to CNN. We want to take the benefit of CNN. So CNN, like they have a shared parameters. So this kind of benefit we want to include in the GNN also. So we want to make a structure similar to CNN, but that easily able to take the graph data. Okay, so this is the motive we want to do. So collective, so like we are passing a graph in the input. These are hidden layers. So after passing this graph, it will do if we pass to all the nodes in hidden layers, then we'll apply leaky value for the non regularity, and then we are passing again in the second layer, then again passing to ReLU, and then we are doing basically we are applying softmax or some other kind of layers to get the output of the graph. Okay, so to doing this thing, we have to first collect the information of the complete graph with the help of message passing, and then aggregation. So there are two terminology mostly are using in GNN. So one is message passing and second is aggregation, combining all the information for a particular graph. Okay, so if I will say what is message passing. So suppose if vector A has some data, it node has some feature. Suppose I'm taking a fixed size for all the features, all the nodes, 5 length. Okay, so suppose, so message passing could be done multiple phases or multiple iteration. So what will happen? Suppose this A want to get the information of neighbor information. So what it will do? It will ask the information by the neighbor's node in the first iteration. So what will happen? This B will send data, this D will send data, this C will send data to this graph or to this node. Okay. So what will happen? This A vector combined with B, C, and D vector. So this called message passing plus aggregation. So this is called, you can say, one iteration. So in one iteration, it's only collecting information from neighbors. Okay. Now suppose you want to take the information from E and F. So what you will do? You will do second pass of iteration, like two hop iteration. So you can say first iteration is one hop. Second iteration is two hop. Hop, I think hop is not a new word. Hop is like simple. This is one hop, two hop, three hop, four hop. From like one device to other device. How many node you have to pass it? That is simply called hop, na? Okay. So this kind of message passing system is there to transfer the information from one side to other side and to aggregate for a particular node, and that information can further pass to the neural network. Okay, so now we are jumping to the embedding node, and then we are going to for the GNN and other kind of variants. So suppose this kind of graph we have, and we want to embed the node in kind of some kind of two-dimensional vector, you can say. Okay, so for embedding the node, we again need to find that if two nodes in the graph are nearby, two nodes in the graph are nearby, then in embedding, they also should be nearby. Or you can simple language you can understand. So difference of two nodes or 2 points in the graph, the difference of distance should be similar after embedding into two-dimensional space. So then we can say it's a perfect embedding, else there is no benefit. It will lose the actual information, it will reduce or to lose the actual inference of the graph. Okay, so this graph could be in three-dimensional, like something is in the upside, something in downside, because we are representing like right now 2D, so it will look like it's a similar, but it could be like something is in the front, something in the downside or upside. Okay, so we want that embedding should be nearer to the node which is actually nearer in the original graph or input graph. That is also mentioned here. Find embedding of node to d-dimensional so that similar node in the graph have embedding that are close together. So for that, what is the setup for that? So assume we have a graph G. V is a vertex set. What we are combining for all the vertex. Okay, and we have A adjacency metric. That basically representing the representation of graph. We can represent the graph with the help of adjacency metric. Okay, and right now we are not assuming any kind of node feature or extra information is used with the node itself. So how we are doing node embedding? The goal is to encode node so that similarity in embedding space is approximate equal to similarity in the original network. Suppose this is our original graph and we are doing it in converting into embedding space, 2D space you can say. Okay, so we have taken two nodes, one is U, one is V, and we are generating embedding with the help of encoder. Okay, encoder could be anything that will like word to back or deep vogue. There are multiple algorithms are there. So after that, we are converting into ZU, ZV. You can say GU and GV is embedding of that particular node. Okay. So now what is the motive? So the motive is the similarity in the ZU and GV should be similar as U and V in the original graph. So this is the goal dimension. Similarity between U and V is approximately equal to ZV and ZU. ZV and ZU. Why we are doing transpose? If anybody can say us, if anybody can tell us. Why we are doing the transpose? If anyone have information, not compulsory. Okay, so I can tell you. So basically, these are two are vector. So if we are multiplying these two vector, it will give us a matrix. So, but we are doing transpose of one vector and then multiplying, so it will give us a single value. So based on that, we can find the similarity score between two embedding, and that should be similar to similarity U comma V. Okay, so that's why we need to define this encoder U and encoder V in this way, that the similarity is closer to the ZGV transpose ZU. This is a learning on node embedding. So what we need a encoder, we need a node similarity. Sorry, 1 second. Yeah, we need a node similarity function, what we are calling it as similarity. So basically this encoder will map a node to embedding. So you can say it's kind of word to vec. Okay, and then we have one similarity function that will basically measure of similarity in original network. So that could be Euclidean distance or anything, and optimize the parameter of encoder so that similarity of UV is approximately equal to ZV transpose ZU. So you can say it's a kind of mathematical formulation for the previous slide what we have told you. Okay, so this again, like you can say, two key component. One is encoder, one is similarity function. So similarity function is this one, and encoder, basically encoder is generating a vector or generating a embedded space for a V node is equal to ZV. So we can say ZV is a d-dimensional embedding for the particular node V. Okay, so I think it's very simple, nothing difficult. If still you have any question, then please ask to me. Okay, so next is how to define node similarity. How to define node similarity. So basically, this key distinction between shallow method is how they define node similarity could be depend on multiple parameters. So maybe if they are connected, maybe they are sharing same neighbors, maybe they have similar structure roles. You can say degree of the node. It could be any parameter. But to find the similarity, I think I missed one slide. There are three, four algorithms are there based on adjacency metric, based on hop base, and third is random walk. So these kind of algorithm will help us to find the similarity of node. So which you can use. So these two are taking basically order of V square complexity, and this is generally taking order of V or order of E. So people are saying we can use random walk for the finding the node similarity. So this kind of encoding, they are saying it's a shallow encoding. So because encoding is just a embedding lookup, or you can say it's assigning a number or assigning a kind of vector or value to a vector. So basically they're saying each node is assigned a unique embedding vector with the help of node to vector function in the Python. So this kind of thing we are doing. So encoding of V is belong to ZV. So suppose there is a node U, or you can say, let me retype. So we have a V node, and from V node we are generating a vector. Could be anything. It's called ZV. Okay. So this is the simple function. Okay, and V is basically of all nodes are existing in the graph, and the total G is, this is a complete G. It's a 2D matrix. Okay, so this 2D matrix is the combination of a vector for all the nodes, a vector for all the nodes, a matrix. Each column is node embedding what we will learn. So there are multiple columns are there. Each column will be embedded with particular vector. So this way you can say it will give you a complete metric which have embedding of all the nodes. So you can see the clear example or clear description. So you can say we have embedding vector for a specific node. You can say it as a V. So we have one vector for particular node, and similarly if we are adding for all the nodes, then we can say it's kind of a Z vector or embedding metric for the graph. So this total number of rows basically dimension or size of embedding, and this is basically for number of nodes in a graph. Okay, so this will give you a 2D metric after the embedding. So what are the limitations for this shallow encoding? The limitation are it need order of V parameter are needed. So they all required separate parameters for their learning. There are no parameter sharing, and every node has its own unique embedding vector. Inherently transductive. So it's impossible to generate embedding for nodes that were not seen during training. If a new vector or if a new node is joining our network, joining our learning, so we are not able to generate a generalized model for that node also. So that we can see in the next one, which we are able to easily generate it. And do not incorporate node features. So right now we are not discussing any node feature. We are just putting a random code for a particular node with the help of node embedding. So the next part we will see like a proper function or that proper code that will help us, that will actually provide us the input feature for a particular node. So we'll see like how deeper method based on graph neural network, how it is doing. That is basically complete function that depend on the graph structure. So these are the basically like we are trying to give you an overview of all these algorithms, basic how GNN is working. Basically, this basic is how GNN is working. Next is then GCN, graph convolution, then graph aggregation, then gated graph. You can say it's kind of RNN applying with the GNN, and then subgraph embedding. So basically, we are not doing for whole network. We are doing it for sample set of network. Okay. So we can see like how we are doing this basic graph neural network. So we have a graph G in which we discussed last time. We have a vertex set, we have agency metric, and we don't have an input feature last time. But now we have an input feature, that is X is basically a vector, RM cross V is a metric of node features. So what actually this node is containing, that is a feature of, that is a complete like that is the complete information of a metric in the X. Okay, so this could be categorical attribute, text, image, data, anything. Okay, and this also have node degree, clustering coefficient, and indicating vector that could be generated with the help of one hot encoding of each node. So this is a setup how we are like going to start our implementation. So first of all, we are going to do a neighborhood aggregation, whatever I told you in the starting slide. Okay, so how we are doing it? So basically, we are generating node embedding based on local neighbors. Okay, so suppose we are generating this like node embedding for node A. Okay, for generating node A, what are neighbors? Local neighbors are D, C, B. Okay, so these are the node which help us to generate their embedding with their own data and with their neighbor data. Okay, next, if we are want to get the value of B, how this B will get the value? B is here. So B will get from A and C. A and C. So you can see what information we need. It's again passing from the system or from this model to the B. Similarly, you can see B is passing from A and C. C is getting from E F and B, and also from A, B, E, F, and D is only passing from A node or getting from only A node. So this is the neighborhood aggregation, how we are doing the aggregation from the neighbor nodes. So node aggregate information from the neighbor using neural network. So what we are doing here, this thing here we are doing some kind of neural network processing or embedding the data after aggregation. Okay, so how we are doing it? So basically network neighbor would define a computation graph. So we have to make a computation graph for all node. So basically they are generating every node define a unique computation graph. So you can see here we are targeting A node, here we are targeting B node, here we are targeting green C node, blue is D node, purple is E node, and pink is F node. So when we are generating a computation graph, so you can see these all graphs have their different computation graph. No one has same computation graph. And you can see this all graph is only generated with depth 2, not more than that. Okay, because in the mostly in level 2 we are getting the same node from whom we are generating this computation graph. Okay, so basically after for doing embedding, we can assign a layer for all the nodes. So suppose this is the initial thing, this is the next one. Okay, so this initial part we can say this is happening at layer 0. So here we are doing aggregation, then neural network, then we are doing it aggregation again at layer 1, and then this final one at layer 2. So nodes have embedding at each layer. So I told you in depth, in each depth or in each layer they are doing embedding. And model could have arbitrary depth. So you can say it will be a hyperparameter for the GNN. Now it's up to you how much depth you want to train. How much depth you want to train. Okay, so you can say layer 0 embedding of node U is its input feature. So what this value containing? This value containing the input feature or input information of a node. That's called XA, or XU means any particular node. So there are two ways, either with the help of input feature or with the help of node to WAC. In the initial time. After that, it will just get it from the previous stages or previous time. Okay, so neighborhood aggregation can be viewed as a center surround filter. And this is like how convolution is working. So we can also try this kind of similar structure in this also. So key distinction and how different approaches aggregate information across the layer. So that was the major contribution by all the authors, how we are doing aggregation and how we are applying for the neural network. So for that, people have applied so many contribution in the last decade, you can say. So what kind of aggregation and what kind of neural network, or how you want to apply neural network, that is the key contribution in this GNN. Okay, so basically basic approach is average neighborhood information. We are just taking all the information and we are taking average of all the information and apply it to a neural network. So we are taking average here before neural network, and after that we are applying neural network in this block. This is basic one. So that's why, like, you can say it's a graph neural network, simple averaging of all the neighbors, and then we are applying neural network. And after that, people have tried so many things. Why average? Why not maximum? Why not minimum? Why not different functions to find the best possible value for the next embedding? Okay, so this is the formula how we are doing this kind of what we are explaining in the theoretical way. It's a mathematical view. So basically, we are taking average neighbor masses and apply a neural network. So this is basically XV. XV means XA. One vector is there, okay, and that is assigned to the HA0. HA means like the previous this state of A vector or A node at 0th time. At 0th time. Okay. So this we are using for the taking all the information from the previous nodes. Okay. So what we are doing, we want to predict for the HA1 next time. We want to predict for the next node. Okay. So how we are doing it? So we are applying the neighbor of node that are basically U. So all the U of previous time. K minus 1 is previous time. Let me this is initial layer. This is kth layer embedding of V, like kth time or kth layer. You can say this is sigma for basically non-linearity, or you can apply ReLU function or tonnage function. This is basically average of neighbors. We are adding all the values and then we are taking average. Okay. And then this is the previous layer embedding. It's equal to HA0. Okay, and these are the two parameters that we have to train during the network, during the graph, or like in the neural network. Okay, I think it's slightly difficult, so I will try to explain you in detail with one example. So I think after that will be clear how we are doing this averaging and all these things. So with this, it will be like easy to understand. So suppose I have taken one network. Okay. So what will be the vector for that in the initial time? HB0, HA0. HD0, HE0, HF0, HC0. Okay. So now what we want to do? We want to suppose we want to calculate for A. Next one. So what is that? HA1. One is clear. Basically, we want to calculate for new node. What is the formula? We are applying sigma, or like you can say ReLU. Okay. Then we are applying a weight. Okay. Then what is the next thing? We have to combine the neighbor node. What is a neighbor node? So we have three neighbor. So what is the value for that? HB0, HC0, HD0. Okay, and then how many nodes are there? Neighbor nodes are 3. So this will be multiplied with weight, and finally with B, one more parameter, with the previous state of the current node, HA0, and then it will be add, and then it will be find for the next values. Clear hai? Similarly, we can also find it for H1B, H1C, H1D, H1E, HF1 for all the nodes. So this is the funda how we are doing it. So now we will just take addition, and then we will divide by 3. So it will be aggregation, and then we can apply or pass it to the neural network with two kind of weight. One is W and one is B. Okay, and suppose you want to calculate for second iteration or second layer, H2A. So what will be the equation for that? Again, sigma, weight metric of 1, H1B, H1C, H1D, divide by 3, then B1, and the previous one, this is 2, the previous one is H1A. So this process will continue again, then we can find H2B, H2C, H2D, then we can find H3A, similarly like H2B plus H2C plus H2D. This process will continue. So it's up to you how much depth you want to go. So this is the example what this equation is telling here, how we can do it in the with some example. I hope it is clear. So after doing this, we can just apply in the model and we can train the model. So for training the model, we need to first define a loss function. So after generating a Z, we can apply a loss function over LGU. So simple this is the basically the same equation that we are using in the previous slide. So this is basically ZV after generating the whole embedding or multiple layer of embedding. So we can pass this information with the loss function. So what that similar thing like what we are doing in neural network, we are doing forward propagation multiple time, and finally we are calculating the loss. So that loss could be back propagate with the all layers to train the weight and parameters. This loss basically again we are using here because we want to make a similar system what CNN is using. So for that we are calculating a loss. So after calculating a loss, we can pass that loss to the previous nodes. I can just show you. There is one function of loss. I can yeah. So basically, like you can see, if you want to find a model, is it human or bot? So in network, is it common problem? Is it a malicious activity or genuine activity or genuine node? So for that, we can use this kind of work for node prediction or node classification. So for that, we will use to apply loss function. I think we have seen the loss function now. Y log y cap plus 1 minus y log 1 minus y cap. Similarly, na? This kind of loss function is using. So similarly, we are using here also. So you can say this GV is basically output embedding. What we are doing, embedding for the node. And then we are multiplying with the theta classification weight, and then we are calculating the loss with the help of output class. With the help of output class, or you can say desired output class, not class label. And whatever the loss is there, that we can that loss we can pass to the previous layers by next epoch. Okay, so basically this is a like overall model design, define a neighborhood aggregation function, and basically define a loss function. Then we can train on set of nodes. So suppose we are targeting A, B, C. We are training the model with A, B, and C. Okay, so training with 3 nodes can help us to generate embedding for other nodes. So there is no requirement to train for other node or train for other embedding computation graph. So that is the benefit of this thing. So one thing is there, this also allows inductive capability. So basically this same aggregation parameter shared for all the nodes. We're not saying like if one parameter is trained for one network or for one computation graph. This is the one computation graph, no? So this one computation graph shared parameter will be also used for next computation graph. So this will be basically helping us to not work on a new node or new network when it comes to the picture without retraining the complete network with the help of shared parameters. So this is the inductive capability. So if we are suppose we are training on one graph, so it will be generalized to a new graph. It will be generalized to a new graph. You can say like if you are training with one snapshot, if new node arrives, automatically we can generate an embedding for the new node. We don't need for train the whole system again. So you can say now we are doing two things. One is if new graph is coming, and one is new node is coming. Suppose we have thousands of videos. If one more videos came, then we can just simply say a new node is came. We can try to find the embedding. And new graph means we have already trained for 1,000 graphs. So can we use the same model for 1,001 graph? So both the things are possible with this kind of network. So that's why we are saying inductive capability. Okay, so this is the work for GNN. Now we can see what kind of different aggregation is possible that we can do, and that is helpful for the proposing different new approaches. That you can say we can apply a different kind of mechanism here to generate different solutions, different kind of efficiency of the model. So first is GCN, graph convolution network. So basically it's similar like to CNN, what they have proposed. So you can see, so this author have proposed a new method for neighborhood aggregation. So they have proposed this equation. So if you remember, what is the difference from previous equation to this equation? If anyone know, if anyone have seen, remember the difference from previous one and current one? Okay, so basically we have removed one parameter, that is B. B is removed, and what we are saying, we are doing directly with all neighbor node and the node itself. So you can say A and the neighbor node is BCD. Neighbor node is BCD. So we will sum all the nodes, and then we will use, or we will basically divide with all the number of nodes. So you can see the difference. Basically, this is the basic GNN, this is the GCN. This parameter is simply removed, and this HK minus 1 is also included here. So here is only NU, here is basically NU and V. So that's why it's saying we will directly combine the parameter of NUN and V. Okay. So basically it's simple. So empirically we found this configuration that given the best result. So it will happen with the help of, because it allows more parameter sharing and downweight high degree neighbors. I will try to show you one example of this. Let me open my previous slide. I can take the example, it's the same example. And picking the slide. So I can show you the same one. Is there any doubt? It's not allowing me to reach. Why? Okay, it is not allowing me to remove. Let me slightly shift it, then I can try.
My apologies, I don't understand.
I think not working. Yeah. Okay. So what we have done with the previous one, if you remember, so what we are doing, HA1 is equal to sigma W0 HB1 HB0 HC0 HD0 divided by 3 plus B0, and here we are doing HA0. So what this GCN is saying, we're not doing this thing, we'll combine all these parameters. So simply sigma W0 HA0 HB0 HC0 HD0, and then divide by 4, and then simple. We will remove this part. So this is the minor change they have done. So actually you can see like this will be basically for different node will be a different values. So this is the major difference in this GCN and GNN. Okay, and this one more implementation they have done with the help of batch implementation, with like passing the batches the data. So they are saying the next embedding of k plus 1 so will depend on the current embedding, the weight metric, and this will be completely multiplied with adjacency metric with DII. You can say diagonal summation of all the values. So in this case, they are saying they're able to reduce the time and they're able to achieve the higher accuracy. This is the one generalized GCN architecture. They're passing a graph. Input graph, they are using 2 convolution layers. We are applying leaky ReLU, then we are applying some kind of dropout, and finally we are applying basically softmax for classifying into particular version. So I think time is coming near, so I can just slightly take faster to the other kind of variable. So that is graph says. So basically, it's saying we not define a fixed function for aggregation. You can say it's average. So we'll take in place of average. We'll try different kind of aggregation. We'll try different kind of aggregation for combining all the information from the neighbor nodes. So that could be possible different kind of aggregation is possible. So that I can just show you the list. So they are saying mean or average. They are saying we can use pooling, pool. So like maybe we can use maximum one, or maybe we can use minimum one, or we can also apply some kind of LSTM approach for doing the aggregation. So this is one more variant of GNN in which they are saying we can define aggregation at runtime. And the one more is there, that's called gated graph neural network. It's kind of recurrent base. Okay, so basically the node meshes, node aggregate meshes from their neighbor using neural network. So they are saying we will basically this graph says and GNN all are working on like they are applying for 2-3 layers. And suppose if you want to transfer it for 50 layers or like a deep network, deep graph, then we can use some kind of memory thing, or you can say recurrent neural network thing in this GNN network. So till now we are doing only with 2 layers, and now we are doing with 10 number of layers. So this help us. So basically, if we are doing with the previous network GNN, it will overfit the parameters, and it will vanishing or exploding the gradients. Maybe it will like too low, or maybe it will too high, because if we are going with too many number of layers. Okay, so basically then they are saying we can use model recurrent neural network for this work. So we are basically in aggregation will apply this recurrent neural network to aggregate all the data from different nodes. So we are applying here RNN module in place of normal module. So you can see we are applying gated recurrent unit, recurrent unit for aggregating the data. This is also similar thing, like you can handle more than 20 layer with this. And one more last is there. So basically, this is like still in the research, you can say, not properly like they have come up with some solution. So they are saying, can we do subgraph embedding? Can we do subgraph embedding in place of whole graph embedding? So like this is the idea. Right now what we are doing, so we are focused on node level embedding. We are embedding from U to ZU. From node U to ZU. Okay, so what about subgraph? Suppose we are saying this is a complete subgraph S. Can we embed a particular graph in the space, embedding space? So yeah, people are saying we can just like sum of all the nodes and then embed into subgraph. But this is not always sure it will be a good mechanism for that or not. So basically they are saying they are introducing a virtual node to represent the subgraph and then run a standard graph. So this is two approaches there. One is we can just simply sum it, and then we can apply for a embedding. And here they are saying we will generate a virtual node from all the 3 nodes, or all the subgraph nodes, and then we are going to generate a embedding for subgraph. Okay, so similarly, like multiple advancement is happening, and still it is like a research area. If we can do a embedding for subgraph also. Any question, guys, till now? If you have anything, I think all our faculty are there. So because I understand this is a new topic, so like understanding from the first time, it's like difficult, you can say. I have one, you can say, Google Colab link. If you guys can want to try it at your home, you can try it. Right now I'm just simply showing some kind of small parameters what are using and how we are doing it. So that's why I've included one lab. I think our sessions till 1 or 1:30. If anyone from organizer. Is Madhuji is there? Okay, let me check the schedule. I think it's till 1:30. I think. Yeah, I've seen. I think it's 1:30. So I can just give a brief demo of the lab in 10-15 minutes. Then you can have any question that you can ask me. Okay. I also include some kind of popular code bases, resources from where I've taken the slides and video resources. So you'll get more insight about that. You can jump to the code. Let me. This is a library. This is a Jupyter file. I think this Firefox browser is also visible now.
Yes, sir, it is visible.
Okay. So basically, this small example is basically showing you how, like, I suppose a molecular is there. So that molecular, what is the chance to resolve in a solution or to mix in a solution? So that probability we want to predict. And actually, this molecular have a structure like a graph. So that's why we have made a basic GNN, or you can say GCN, to implement that. This is a sub-component installing PyTorch, geometric RDKit, background information of dataset. We'll just see that how dataset will look. Then we're converting this string to RDKit module. Then we're implementing a GNN. Then we're training it. Then we can try for the improvement. So I will just give you a brief overview. Later you can just download from the slide. I have also mentioned a link. If you just open the link, it will open automatically in your system. And then you can do some kind of hands-on with this kind of lab. So we are downloading two packages. So one is PyTorch Geometric and second is RDKit. So PyTorch Geometric basically will help us to build GNN, or you can say this PyTorch is giving us the inbuilt capability for the capability for using inbuilt function of GNN. And RDKit is basically handling the graph data, or you can say molecular data for the particular molecular. So that you can use RDKit. Okay. To work on that, we'll install this torch version. So I'm not executing the command because it will take time. I've already executed the commands. So after this, like this installing torch, it will give you some issue of you can say version. And be careful, runtime to execute this file, change the runtime type to GPU if it is CPU by default. Okay. To install this torch, we need a kind of conda, or you can say mini conda. So first of all, we are installing a mini conda. Here you can see after installing mini conda. So it's simple, like you have to just press enter, nothing you have to see, take care. So after that, we can install torch again. It will remove all the dependencies during the installation. Okay. So after installing this, we can see what kind of dataset we are using. So basically, in this following dataset, we are using a dataset collection of PyTorch geometric. So this PyTorch geometric have multiple data set for different you can say different applications. Okay, so when we are taking one data set that called molecular collection data set, which you can see it from this location. Okay, what is the information, what are the parameters, what are the features, and how they are connected. So all the information can be directed from this link. So this dataset name is basically ESOL. So ESOL is a small dataset consisting of water solubility data for 1128 compounds. So here these graphs are basically 1128 compounds we have in the dataset. The dataset have been used to train model to estimate the solubility directly from the chemical structure. So we are just checking the solubility, is it possible or not? And if it is there, then what is the solubility? So note that these structure don't include 3D coordinates, since solubility is a property of molecule and not for its particular conformer. So we have a solute and we want to mix it with solvent and we want to see how much solubility is possible. So this kind of data set is existing. So this is the basically structure of a particular solute, how this solute will look like. So you can see this kind of structure can be easily represented or demonstrate with the help of graph or network. Okay, and this is also like a string form we have mentioned. What is the data is actually showing in the figure. Okay, and you can say, sir, why can't we use the string directly in passing in RNN? But actually we don't need only the string, we need actual the connections of graph, what will be the inference for that. So that inference basically actually will be helpful to finding that is it what is the probability for that solution will mix with the water or with solution or not. So that's why we are using GNN, not simple RNN or CNN. So for that, we are basically importing the data set. The data set, we are downloading it from this website. And we have this ESOL data set. The total number of rows are 1128. We are basically going through the data set. What is the type of data set? How many features are there? So if you want to see a data set, you can click here. Okay, it will give you a CSV file. I have already downloaded it. So you can see this is the CSV file of the dataset. This is a compound. This is the ESOL predicted logs solubility, then minimum degree, molecular weight, number of H bound, number of rings, number of rotatable bonds, polar surface area. Then this is the final class, major log solubility in moles per liter, and this is the structure of the particular molecular. What is a smile? Basically, they are saying. Okay, it's have 734 targets. If we're talking about particular sample have 68 edges with the nearby nodes. And how many nodes? 32 nodes. And this is the smiley of that node. Okay, so this is the structure. What is the X? X means input feature, and output feature is Y 1 cross 1, simple one number. You can say probability of solubility. This is the input feature, you can say structure of graph, that is 32 by 9, 32 rows and 9 columns, because we have 9 features. So if you want to see the X, and simply print data 0x, it will show you the 32 cross 9 rows. This is similar what we are showing in the experiment. And if you want to see the edges with this data 0, you can print the all edges. So it will be around 63 edges with this node. And if you want to see a target is Y, that is basically minus 0.770. So we want to predict that value after this complete training and testing. So basically, there are two kind of things could be possible. We can predict a single value after the complete analysis, or we can predict a node value. So both things are possible. What I told you in the starting, either it can be used for node classification or it can be used for graph classification. So then it's like their detail are there for converting smile into RDKit. So basically this is smile, this is the actual structure of the data 0, how it will look like. So it's kind of molecular, what we are trying to predict the solubility of the molecular. Then we are implementing a GNN. It's like similar like what we are implementing with CNN. So we are first of all initializing the layers. So initial layer with the number of features, then embedding size, then we are using 3 convolution layer, and then 1 output layer. And then we are in between, we are assigning the what we are saying, this non-linearity function, this 10H with all the layers. Then we are applying for global pooling with all the data. Okay, and then we can go for directly for training of GNN. So for training of GNN, we are first defining the GPU for the device. If we don't have, then we can try it on CPU, but it will take time. Then we are applying Atom Optimizer for calculating the loss. Then we are defining data. So this load data basically for training, and then we are defining one test data for testing of data. So what we are defining, we are saying 80% data for training and 20% data for testing. And we are doing a training on batch wise. So we are defining a batch of 64. So we are taking a 64 data from the train loader, then we are assigning to a device. Okay, then we are basically assigning the gradient to 0. Then we are, with the help of PRED, we are training the model. At the same time, we are also calculating the loss of the model. And we can try this training of the model for 2000 epochs. After training for 2000 epochs, we can see this loss is continuously decreasing. Yeah, you can say you can try a different kind of version because there is multiple spikes are there. Up and down is existing. So we can try to improve this model with different kind of hyperparameter tuning. Okay. So then we can try to text the data with the help of text loader. What we have assigned 20% data. So 20% data we have applied in the form of one batch, and then we can get the value of what is the real value and what is the predicted value. So you can see we are reaching somehow near. It's saying 3.2, we are getting 3.5, 8.4, 7.5, 0.3, 0.9. Somehow we are getting near to the near to the actual output, and we can check the how much nearest is there with the help of this plot. And yeah, we can also improve the model with the help of different kind of parameter tuning, dropout, pooling layers, global pooling layers, batch normalization, other multiple layers, hidden size layer, and then test matrices in hyperparameter optimization. So if you want to go in more detail, you can see this complete file that I've shared in the hands-on link. So with this link, you can easily download or easily open in your Google Colab platform, and then you can try this. It will just simply, it will take around 20 to 25 minutes for complete training this file. So I can stop here my topic. I hope you get some insight with this lecture of graph neural network, but I tried to cover in this session. I understand this is a slightly, you can say, a new topic. So maybe you can say it's a slightly difficult one in the understanding the first go. But I hope it will give you a flavor of the GNN and what kind of application can be used for implementing this GNN and how it can make our life easy in the case of if we have a graph like problem, like for the.
You can post your queries on the WhatsApp group.
Okay, yeah. If you have any query, please let me know.
Any question from any of you? किसी ने रेज किया? सर हैंड रेज नहीं है.
I will also share the PPT and the notebook.
हाँ,
So
yes sir. You share us PPT and all the material. We will share to all the.
If any query is there, you can mail to me also. If you don't have it right now.
And any of you have any problems anytime, Anna, you can mail to the Gaurav sir. Anna, he is always ready to help the people.
Sir, can we find the data set for SDN network?
SDN network?
Yes, sir.
I think it's out of what we are discussing here and what you are asking. But yeah, I have SDN data set. So you can mail me. I can try to give you link.
Okay, okay.
So my mail ID is gauravsingal789@gmail.com or gaurav.singal@nsut.ac.in. So you can find it anywhere.
Okay.
Yes, dear participants, if you have any query, please raise your hand. I think there is no query, sir.
Okay, thank you.
Okay, thank you very much, sir. It's a really informative session and it will definitely help the participants for their future work. Thank you very much, sir.
Thank you, Madhuji. Thank you, organizer, for giving me the opportunity. Thank you, sir.
Thank you, Gaurav sir.